let's talk about one of the biggest, most mind-bending ideas in all of physics, spacetime. It's this grand stage that contains, well, everything. Everything that's ever happened, everything that ever will. But in that absolute infinity, where are we? How do we find our own little here and now?
You've probably heard this idea that space-time is this giant, all-encompassing block. But if you think about it for a second, that raises a huge question. If the past, present, and future are all just there, existing together in one big structure, then where exactly is the moment that we call right now?
To get to the bottom of that, we first have to really wrap our heads around what physicists even mean by spacetime. So let's start with what I'm calling the universe's empty map and figure out why this map seems to be missing a pretty crucial detail.
Right, so a lot of us have this picture in our heads of the block universe. And it's a cool idea. It's this perfect four-dimensional map that has every single event already drawn on it, from the Big Bang all the way to the very end of time. It's all there at once. But here's the twist. As the folks at Physics Libertex put it, nature dictates no coordinates. We lay them on. You see what that means? That perfect, all-knowing map? It comes completely blank. There's no built-in grid, no cosmic GPS, no lines of latitude or longitude. The map shows every place you could possibly go, and every moment you could possibly experience. It's all there. But it's missing that one thing you always look for on a map at the mall, that big red dot that says, you are here. There is just no built-in, universal now in the fabric of space-time itself.
Okay, so if the universe doesn't give us a marker, how in the world do we find our place? Well, that's what we're jumping into now, how to add your own "you are here" sign, and how physicists actually go about pinpointing their location in this huge, unmarked universe.
The secret sauce here is a little something called an observer. Now hold on, because when physicists say observer, they don't mean some guy in a lab coat with a clipboard. Nope. In relativity, an observer is the extra stuff you have to add to the map just to define a location. It's not a person, it's a set of tools. So what's in this toolkit? 3 really important things. First up is your worldline. That's just the unique path you take through the 4 dimensions of space-time as you go about your life. Second, you need an ideal clock. Think of it as your own personal stopwatch, ticking away time just for you. And third, you need a local frame, which is basically your personal compass that tells you which way is up, down, left, and right where you are. Now, let's really focus on that clock for a minute, because this is where things start to get seriously weird and counterintuitive. It's time to see why time is personal and why we have to completely ditch this old idea of a universal clock for our own personal stopwatch.
You know, MIT OpenCourseware says it perfectly. Proper time is belonging to oneself, the time that this observer measures. The time that your personal clock, your stopwatch, measures is what physicists call proper time. It's fundamentally, completely, and totally your own.
So let's break that down. You have coordinate time, which is kind of like the grid lines we just draw on a map. They're just labels, they're not real. But then you have proper time, and that's what your personal stopwatch actually measures. It's a real thing. It's like the miles on your car's odometer. It's the actual, unchangeable record of the journey you took. So here's the absolute key takeaway. The question, how much time has passed between 2 events, is actually a trick question. It's meaningless on its own. You have to ask, for whom? You have to pick an observer's specific path through spacetime, their world line, before you can even begin to answer that question.
And get this whole idea doesn't just stop at time, the exact same logic applies to space. Which brings us to the physicist toolkit, where we're going to see that even our basic ideas of space and now are actually choices that we have to make. The physicist Eric Gorgulhan really nails it. He says that splitting up that 4D block universe into 3D space plus 1D time is not something the universe does for us. It's a choice, a rather arbitrary choice that we make. It's how we decide to slice up the map to create a now for ourselves. And hey, Einstein himself was all over this. He was super clear that those coordinates we draw on the map, they have no independent physical meaning. To him, they were just mere numbers. So when do those mere numbers finally get some real meaning? Well, it happens when you anchor them to reality. When you can point and say, okay, this number on my grid lines up with the end of my physical measuring stick,
Or this number corresponds to a real tick on my physical clock. Without that hands-on connection, it's all just a bunch of abstract math. All right, we figured out that the space-time map is blank, and we've seen that we need our own special toolkit to find our way. So let's put it all together in our final section: space, time, and the anchor. This is going to give us a whole new way to think about our place in the universe.
So, to really describe reality in a way a physicist can work with, you need three things. First, you need space. That's the basic structure that lets us have ideas like distance. Second, you need time, the structure that gives us cause and effect and lets us measure how long things take on our personal clocks. And third, the really crucial piece, the anchor. That is your specific, chosen here now, your world line, your clock, and your compass, all bundled together.
Now let's be super clear on this. This anchor thing isn't some new mysterious fifth dimension, not at all. It is that extra structure, that observer's toolkit we've been talking about, that you absolutely have to bring with you to make the map useful for actually navigating and measuring things.
And that right there brings us to the final, most important point. As a piece of pure math, pure geometry, space-time is complete. It's a perfect 4D object. But, and this is the big but, as a basis for doing actual physics, for answering where am I and what time is it, it's fundamentally incomplete. It needs you, the observer, to give it a frame of reference.
So, we'll leave you with this to chew on. We've seen that to get any meaningful measurement, to pin down a here and a now, you have to bring an observer and their toolkit into the picture, which leads to a pretty deep and fascinating question. If a measurement requires an observer, what does an unobserved universe even look like?